Thank you. Thank you. So first of all, I would like to thank everyone joining today because this is a very special event. This is one of the first ones, well, actually the one I've been to, but this is one of the first ones after the COVID times. It was rough for all of us, and I'm glad to see so many familiar faces and new ones as well. So a round of applause for you guys, for you to be here, and it's awesome. Thank you guys. So today, I have a special topic very dear to my heart, which is managing application state. And I said with science because we're gonna just like weave in some hard topics from computer science for this more of a front-end related talk. And first of all, I'd like to talk a bit about myself, of course. Well, I'm Peter Czibik, and you can find me on Twitter, GitHub. I'm a software engineer working in R&D for the past few years. And what I'm going to talk about today is that managing application state, you probably already know it's not easy at all. We tried. If you take a look at our GitHub, we have a project called React Easy State, which is kind of a lie. Managing application state in React especially is not really a super easy topic. We try to make it easy for people to use, but it wasn't really easy to implement. And so there's a famous quote from Phil Carton, which people say a lot. There are two hard things in computer science. One of them is cache invalidation, and the other one is naming things. And I think we could add a third one to the list, and that would be state management. Because I think that could compete for the third place in that list, because that's not easy. And today I'm here so you can learn about yesterday's tech, science, and apply it to your problems that are going to arise tomorrow. And let's see. This is our agenda today. First, I'm going to talk a little bit about what is state management. You probably already know, but I would like to give a refresher for those who are not super familiar with it. And then we're going to talk about finite state machines. That's going to be the more scientific part of it. And then we're going to apply that to some real-world problems and see how that can solve how that can give you some real solutions to your problems. And so, state management. State management can be best described with a quote from a series from the UK called IT Crowd. I'm sure probably a lot of you are familiar with it. And they used to ask this all the time. Have you tried turning it off and on again? And that is because state management, state in general, is all the moving parts in your software. And when you reset those moving parts in the software, then you can get into a predictable state. Because most of the time, when you're implementing software, when you're building machines, it's that the initial state is the easiest to understand. And that's why they're saying this all the time. Turn it off, turn it back on, because initial state is the most predictable, to most people at least. A running program can have many moving parts and many incremental states, like small states, like here and there, and then predicting what state the application is in as a whole is a really hard problem. Inspectability and debuggability matters a lot when it comes to like figuring out what the problem with a software is at the point of time. So it's usually all fun and games until someone decides to write. Usually if you have read-only states, so things that you're displaying in the UI, if you think about React components, for example, if you have props, you can usually tell what's going on in a React component. But when you have a use state, for example, use state hook, it gets a little bit more complicated to decide what state the application is currently in, what is going to be rendered, if you think about in that context. And so read-only states are easy to predict, and if someone decides to have like a piece of state that lives in like a use state callback or something like that, then it gets problematic. And so state is the data in our programs. State is basically what is the data that we need to perform some things like read and write operations, event handling, and you really need to decide if this goes in a global state, if this goes in a local state, and things like that. And we programmers try to think about these things in an organized way. So you shouldn't really, you shouldn't really put some piece of state here and there, and then someone else comes around and they can't really figure out what's going on in the program. So we're trying to organize things properly. And this is the most common, like 95% of the applications out there do this thing. Application is idle, it's rendered, you open up a web page, it's there, it's not doing anything, and then the user clicks a button, you fetch something from an API, save the response, and then present it on some sort of UI. And this is what happens most of the time. Most of the applications out there use this exact pattern. And this is the user's response to this. They try to, like, it loads slow, and then the user starts to click the button, and hey, I want this piece of software to work. And then this is what happens. You have idle state, the user clicks the button, you're fetching the JSON from the API, and then in the middle of that, the user clicks the button and it triggers again, and then you get into like some sort of loop, and also like it triggers fetches multiple times, and it saves response, and some part of the UI is, if you think about it in a React context, you're like, if data is available, then you render this. If there's loading here, you're loading. And then you can get into some real problems. So these transitions, so especially this one and this one, they shouldn't be allowed. And that is going to be really hard to enforce. Like, your colleagues are going to be like vultures looking for their prey, and then they're going to be looking for when they can break these constraints that, oh, hey, I want to fetch here, I want to fetch there, they're just not doing the right thing. So these are, in regular application programming, these constraints are going to be really hard to enforce. And I was like, I'm sure science figured it out so long ago, so let's try to find something that can provide a solution to this problem. And this is what I found: finite state machines. Let me talk a bit about them. Finite state automata, as they are called, is a suite of well-defined states and transitions in between those states. So like, you define multiple states. I'm going to give you examples. Don't worry if you don't understand yet. But you define a few states, and you define transitions in between those states. And there's a very important constraint here that can only be one. So your state machine can only be in one of these states, and the number of states has to be finite. That's where the name comes from. And so these automatas are defined by a list of states, so how the application can work, an initial state, so where it will start from, and the inputs that trigger each transition, because otherwise your program wouldn't be really interactive. People wouldn't really use it that much. So you need all these three things in order to have a finite state machine to work. To illustrate, I think the best thing I can give you is a traffic light. And in a traffic light, you start with the state of, well, you can start from any one, but we start with this state that is red, and then there is a transition from red to green, and from green to yellow, and from yellow to red. And these transitions are triggered by timers. So time passes, it goes from yellow to red, and so on. And the traffic light is actually a very simple appliance that can be represented with a finite state machine. I can give you another example. I can give you another one. But before I give you another one, I would like to tell you that there are so many representations of finite state machines that you can use. There are these state event tables. I'm going to show you an example for that. UML and SDL. And you can use like your creative drawing like I did. This is not super standard, but I think it gets the job done. So I can give you another example. This is a coin-operated turnstile. It's a thing which, when you go to you go to a bar and you have to go to the restroom. Usually you have to put in a coin in some places of the world, at least. I've been to Austria last week, and it was all fun and games, but it was always like this if you wanted to go to the restroom. So the thing is that it's in locked state. That's the initial state, if you take a look at that. If you try to push it, it doesn't work. It goes back. It's a transition that makes it go back into locked state, so it stays locked, actually. And as you insert the coin, it goes into unlocked state, And when you try to push it, you can push it once, and then it gets locked again. So you push it once, and then it goes back into locked state. So these are the states, locked and unlocked, and then you get the transitions like push and insert coin. And basically, this is how you would define the turnstile, coin-operated turnstile with a finite state machine, or at least a representation of it. This is a kind of state event table that I talked about. This represents exactly the same thing, but it's just in a different format. Some people prefer this, and some people like me prefer the graphical way, because I'm more of a visual guy, but that's really up to you. And although the number of states are finite state machine, the possibilities when building software with them are going to be endless. You can do so many things with them, and I'm going to show you examples on how to apply them properly. But before we get into that, we're actually using finite state machines every day. All of the regular languages are defined and processed using finite state automatas. And that's actually one of the definitions for regular languages, that they can be described with finite automatas. And this is actually a definition of JSON. If we take a look at this, is a string part of the definition of JSON, which is defined in some similar way as we would define a finite state automata. So actually, most of the language processing that is out there are already using this thing. So if you're using a compiler, most of the compilers have some related technology like this. So how about we start applying this same concept to our original problem? Our original problem looked like we have an idle state, and then the user clicks a button, we fetch a JSON from the API. If you want to port this over to some representation of a finite state machine, that would look exactly like this. We have states like idle, fetching, loaded, and error. And all of these are represented as states, and the transitions between them would be like start fetching. So when we are in idle state, we can start fetching, and then we're in fetching state, we can, the fetch is going to be done at some point, and then it's going to go into loaded state. So remember, it can only take one of the finite number of states, and we can trigger these with events. And that is exactly what we are going to do. Let's enter the world of XState, which is a library that merges the world of finite automatas and JavaScript. So it's a JavaScript library that implements this exact thing. And the cool thing about this is not just that it implements this thing, but also it has a powerful visualization tool that you can use as a debugger, which is super cool. I'm a visual guy. I'm really into that. So visual debugging, that's one really good thing that we have, and also like it provides you that way to not get into unexpected states. And let's see, let me give you something that this visualization tool is actually based off of a paper published in 1987, so it was quite some time ago, and it's based off of this paper, and the visualization and everything that is done is basically, it's been already figured out, so you don't really have to think about that. And so XState is a library that has many moving parts. We have core XState, we have FSM, and actually it wouldn't be much of a nice thing without actually hooking into React, well, pun intended, hooking into React and also Inspector that would visualize things for us. So if you're using the combined versions of these libraries, you can get into a state when you're like really when you're building a program in React, and then you have all of these tools at your disposal, and you can use that to visualize, you can use that to enforce these things. And let me show you a quick example. We can go back to my hand-drawn chart, but this is my example here. If you take a look at this, we have a machine, and that machine has its initial state. That's very important. I told you that was one of the constraints that we're going to have. So we have initial state, we have the list of states here, we have the state idle, and then we define the transitions with the on keyword here, and then what we can have is we define a transition that when we are in idle state and there's a start fetching transition happening, then we are going to be transitioning into fetching state, and so on. If we take this code and apply it install XState React, install the inspector, do everything right, you're going to end up with something like this. This is something that is generated off of a real running program, well, running on the side here. So I took the code that I've shown you before, and it generated this nice diagram, which is super good. You can take this, you write your code, you take this, you give this to your colleagues when they're reviewing your code, and they can check what state the application may take, because all of the states that are not listed here are going to be invalid. There's not going to be any state other than these ones. Idle, fetching, loading, and error. These are the only states that your application can take, none other. If they can take any other, that's a bug in XState, so you should report it on GitHub. So I think this is a very powerful tool. You can use it for real visual debugging. And in XState, you can actually use multiple of these machines, so you can break up your application in multiple of these state machines. Multiple of the components can use their own state machines to represent their own state, and so you can combine all of these to build a real complex application. Because I'm sure most of you have thought about, like, well, this is not a real whole big application, but this could be one part of your app. This could be like just the fetching logic. You could implement it in XState, and then you can use some other tool to manage the state of the other things otherwise. But the cool thing about this is that you can combine these multiple finite state machines, so you can have a real complex application. And I have a demo, and I'm not really betting on the demo gods today, but at least I'm betting on YouTube, and I hope it will work. I built a small app, which is a Pokédex. Those of you who were born in the 90s will know for sure. But the thing is, well, that's not mine. But the thing is that we have this here. We can click next page, and we can click previous, and if you take a look there, well, it's a bit small, I'm sorry, but trust me, that's previous page and next page transitions. If you click that button, it will trigger a transition from the previous page and next page, which leads back to the loading state, and then the loading state is actually loading something from a JSON, and then we can go into selected state if we select one from this list, and then that's going to add something to the state. And let's wait one extra loop, because it's going to be really hard to follow. But the thing is that when we pick one from this list, there's another part of the system which has its own finite state machine, which is responsible for loading Firo, which is a Pokemon, or Pikachu, which you probably already know and love. And you select something, and then it triggers another part of the system, and then it loads. And so in this way, you can combine multiple of these finite state machines to represent your whole application state, and define all the transitions between them, and all these transitions are going. So there cannot be anything happening in your program without your supervision, without you knowing. The application cannot get into a state which is invalid. And that's what I see most programmers get wrong, is that you don't really think about error states. You don't really think about loading states and displaying everything properly on the UI. Well, some people do, but it's a lot of work. But with this framework, that's basically given for free. And I think having multiple of these finite state machines, breaking this up into smaller problems, breaking this up into smaller states, allows you to just focus on one part of the problem and then combine them into one. With this framework, it's just possible, and there's not going to be any more of it works on my machine, I couldn't reproduce the issue, I'm sure I've tested all the scenarios. Sure, this is some quotes from programmers around the world. I mean, I wasn't expecting this. With XState, and if you're using finite state machines, it's impossible to get your program into a state that you don't really know. And so I think this is a super cool framework that you should try, but please don't rewrite your application with XState tomorrow. Thank you for your attention.